Okay, this is 4-4, day 2, the fundamental theorem of calculus continued. We're going to start out with a couple more definite integrals, but we're going to throw some trig functions in there. Again, the process doesn't change. We're trying to find the antiderivative and then plug in our upper and lower limits and find the value of the integral. So just we're throwing some trig functions in here. So on this particular one, I know that the antiderivative of 3 is 3x. Secant squared, I know its antiderivative is tangent. And then we're going from negative pi over 3 to pi over 3. Oops, positive pi over 3 up there. All right, so we're going to plug those in. So 3 times pi over 3 is pi. Tangent at pi over 3. Okay, now I got to use my knowledge of the unit circle to figure that out. Tangent at pi over 3 would be the square root of 3 over 2 divided by a half. So basically the square root of 3 over 2 times 2. So that comes out to be the square root of 3. Minus, when I plug in negative pi over 3 there, I'm going to get negative pi. And tangent at negative pi over 3, so again, thinking about the unit circle, there's positive pi over 3, negative pi over 3. Tangent down there, the signs are positive, negative, so tangent there is going to have the same value, only it's going to be negative square root of 3 there. Okay, so if I change this minus now, basically both of these are going to become pluses. So I'm going to have pi plus pi, so I have 2 pi. And then square root of 3 minus negative square root of 3 becomes 2 square root of 3. Okay. Can't combine those together. I could take out a 2 if I wanted and make 2 times pi plus 3. But that's about as far as I can go non-calculator there. Okay, here we have cosecant times cotangent. Okay, we know the antiderivative of that is negative cosecant theta. Excuse me. All right, so the integral of that is negative 5 cosecant theta from pi over 4 to 3 pi over 4. All right, I'll just take the negative 5 out, and I'll just plug the plug 3 pi over 4 into there. So cosecant of 3 pi over 4 is the reciprocal of sine of 3 pi over 4. So sine at 3 pi over 4 is square root of 2 over 2. So here this would be 2 over the square root of 2 minus. And then cosecant at pi over 4, reciprocal of that would be also square root or 2 over the square root of 2. And then obviously here, since both of those cancel out, I just get 0. 0 times negative 5 is 0 for my integral. So what happened in the case of this one is we had the same area above and below the curve for this function from pi over 4 to 3 pi over 4, if we were to graph that out. Okay, then we have a new thing to do in section, or the second day of chapter 4, section 4. It's called finding the average value of a function. Okay. If f is integrable, so it means if we've got some function that we can integrate on an interval from a to b, then the average value of that function on the interval from a to b is found by taking 1 over b minus a multiplied by the integral from a to b of f of x dx. So it's basically finding the value of the integral, all right, which gives you kind of the area of the function, and then you're timesing that by 1 over the change in the interval. So basically you're dividing by the length of the interval, your value of your derivative, which is going to give you the average value of the function. Okay? On our example here, I'll show that how that's done, and then I'll show visually what's going on there. So first of all, it says find the average value of this function on the interval from negative 1 to 2. So I'm going to integrate that function from negative 1 to 2. And I'm going to multiply by 1 over the change in the interval from b to a, so 2 minus negative 1. So I have 1/3 times this integral. Go through and calculate that out. So the integral is 3/4 x to the 4th minus 2x from negative 1 to 2. All right, so I have 1/3. I'm going to go ahead and plug in 2. So 2 to the 4th is 16, divided by 4 is 4, times 3 is 12. 2 times 2 is 4. Minus, got to plug in negative 1. Negative 1 to the 4th is just 1, so that's going to become 3/4. And 2 times negative 1 is going to make that a plus 2, because the minus 2 and the negative 1. All right, if I work that out, I end up with 1/3 times 21 over 4, which works out to be 7/4. Okay, now what did I just figure out? Well, if I take this function 3x cubed minus 2. That's going to cross the y-axis at negative 2. At negative 1, the value of that function is going to be negative 5. At positive 1, the value of that function is going to be 1. At positive 2, now that's going to go way up. 2 cubed is 8, times 3 is 24, minus 2 is 22, so that's way up here somewhere. And basically what we have is
Autumn
function looks
Johnson,
like that.
Lemieux to the office, please. Autumn Johnson, Lemieux to the front office.
Alright, so if I were to take that function and I were to calculate, and I were to go up to 1.75, what we just calculated was 1.75 was the average value. So let's say here's 1, here's 2, 7/4 about right there. Okay? If I were to draw a horizontal line at 7/4. Because the average value is the average value of the y values for this function, or the average f of x value. If I were to calculate this area right here, and this area right here, that is above and below that horizontal line, those two areas would cancel out and make 0, basically, if I was using this as my, basically kind of thinking of it as my x-axis. The amount of area above and below that value of 7/4 are going to be equal, making 7/4 the average value of this function from negative 1 to 2. That's what that means visually. Okay? To calculate it, simply take our function and integrate it from a to b and multiply by 1 over b minus a. Alright, then they're going to ask you to calculate the value guaranteed by C based on the mean value theorem for integrals. Now we had our mean value theorem when we did derivatives. Okay, now we have this other mean value theorem when we're talking about integrals. Basically all we're doing here is calculating, on the last problem we calculated the average value. What we're doing with the mean value theorem then is we want to calculate where did that average value happen. So see how I have 7/4 here on the vertical axis and it intersects my curve? The question would be then where does that cross down here? Okay, or I'll put a C right there. Where does that cross the x-axis? Where did that average value happen? Okay, so you'll notice with the mean value theorem, it starts out by saying the mean value theorem says the integral from a to b is equal to f of c times b minus a. Or if I rewrite that, I get f of c is equal to 1 over b minus a times the integral from a to b. Basically, this is the average value. Okay. And what this theorem says is that if f is continuous, and there exists some number c, okay, where our function is equal to that average value. Okay? So for example, up here, I found that the average value was 7/4. Now I want to figure out where did that happen. Well, I take my function, I'm going to replace x with c, and I'm going to set it equal to the average value. I'm going to add 2, which gives me 9 for, if I add 2 here, it's going to be adding 8/4 to this. So that's 15/4. I'm going to divide that by 3, which is going to make it 5/4, because I'm basically timesing by a third. And then I'm going to take the cube root of that. The cube root of 5/4 comes out to be about 1.077, which is where that value happens, where when I plug it into the function, I get the average value of our function. That's all we're doing with the mean value theorem, is once we get the average value, we're going to take the function and set it equal to that average value and find out where that happened. Okay? As long as our function is continuous, we can do that. So let's apply that in this situation. It says find the value of c guaranteed by the mean value theorem for integrals for this function over the interval from 1 to 4. All right? So first of all, I'm going to calculate the average value. Average value, remember, is going to be 1 over b minus a, so we're going to have 1/3, integral from 1 to 4. Now I'm going to go ahead and rewrite this before I try to do its integral. So 4 over x cubed, I'm going to rewrite as 4x to the negative third, and x cubed over x cubed is 1. Okay? I'm going to go through and integrate this. We have 1/3. When I raise this to the power of negative 2, so I'm going to have 4 times x to the negative second divided by negative 2 plus x from 1 to 4. So I'll move that over there so you can see that. So I integrated the x to the negative third by raising the power by 1 and dividing by negative 2. And 1 became x. I'm going to clean this up before I try to plug my numbers in there. So 1/3, we have negative 2 over x squared, when I clean that one up, plus x from 1 to 4. All right, plug in my 4. So I have negative 2 over 16. That's negative 1/8 plus 4. Plug in 1, we end up with negative 2 plus 1. All right, if you add that stuff up correctly in there, you will end up with 39 over 8. Then 3 goes into 39 13 times. So I've calculated the average value to be 13 over 8. Now I want to know, where does that average value happen? So I'm going to take my equation, 4 plus c cubed. I'm just replacing x with c. If you want to leave it as x and then just change to c at the end, again, that's fine. So you got that. If I then cross multiply, I get 32 plus 8c cubed is equal to 13c cubed. If I then subtract the 8c cubed, I get 32 is equal to 5c cubed. I'll divide by 5 and take the cube root. And that's equal to c. Okay? Now I could clean that up a little bit because 32 is 2 to the 5th, so you might see that answer written as, let's see, since that's 2 to the 5th, I can take a 2 out with a 2 squared left inside, so it'd be the cube root of 4 over the cube root of 5. Now you might say, well, how do I clean up that radical? Okay, well, remember the cube root of 5 is 5 to the 1/3. If I had to clean that up, that means I would have to multiply the top and the bottom by 5 to the 2/3.
Autumn Johnson Lemieux to the main office, please. Autumn Johnson Lemieux to the main office.
Sorry about the announcement interruption there. All right, so if I had to do that, then I would end up with, let's see, on the bottom here, I'm going to have just 5, because 5 to the 1/3 times 5 to the 2/3, so 5 on the bottom. And then I have 5 to the 2/3 and 4 to the 1/3. So basically I have the cube root of 4 and I have the cube root of 5 squared. I can multiply those together and get the cube root of 4 times 25. That would be the cube root of 100. Okay. So that's how I would clean up the cube root of 32 over 5 if I had to simplify it. Won't necessarily make you simplify that, but if I had to, okay, cube root of 5 on the bottom is 5 to the 1/3. I have to multiply top and bottom by 5 to the 2/3. So I got a cube root of 4 and basically the cube root of 5 squared. So the cube root of 4 and the cube root of 25 makes cube root of 100. Okay. Let's just see what our decimal approximation was on that one real quick. So 32 over 5 to the 1/3 power. It's about 1.857. And you can see that that is in our interval from 1 to 4. Okay? And you should get an answer that is in your interval. If you don't, that means either your function wasn't continuous and the theorem didn't apply, or you made a mistake. Okay? All right. Next one, before we get into this second fundamental theorem of calculus, I want to go through this problem right here and then explain how this applies to the second fundamental theorem of calculus. It's kind of a weird problem. It says we're given a function, but that function is actually an integral of some function. In this case, it's 2t plus 3 times dt. And then our limits are from 3 to 2x. So the weird thing here is you have limits that aren't defined values. One of them is a variable. Okay? Your function is with respect to another variable. Okay? And then f of x is the integral of this function from 3 to 2x. And then what we want to find is the derivative. So we have a function that's given to us as an integral, and we want to find its derivative. All right? Let's go through the process first, and then we'll talk about how you can use the second fundamental theorem to do this. Okay? All right, so first of all, if I were to integrate this function with respect to t, so not paying any attention to limits right now, if I was just going to integrate this with respect to t, because it's dt, 2t would become t squared, and 3 would become 3t. Okay? Now I'll put my limits in there. So we have 3 and 2x. Okay? So f of x is still equal to what we've found right now. Okay? If I plug 2x in there, 2x squared becomes 4x squared. If I plug 2x in here for t, I get 6x, so 4x squared plus 6x. Minus if I plug 3 in, I get 9, plus another 9. So right now I have that f of x is equal to 4x squared plus 6x, okay, minus 18. All right, so there's what my function is. Now it says to find the derivative of that. So now I've integrated, I've plugged in 2x and 3, I've simplified it down, and then I want to find the derivative of that. Derivative of that comes out to be 8x plus 6. Okay? All right, we can do all that. We can integrate, we can plug in 2x, we can plug in 3. But second fundamental theorem gives us an easier way to do that. Okay? If I don't know why that says if that, but if f is continuous and on an open interval containing a, and f of x is some function where we're integrating from a to x of f of t dt, well then the derivative of f of x will just be equal to f of x times dx. Okay? Now what we're going to do is we're going to apply this theorem to the same problem we just did to see if it works out. Now the key thing is here again, we have a constant to x, and then we're integrating some function f of t dt, so basically with respect to a third variable. But to find the answer, all we have to do is plug in x for t, and then take the derivative of x. Okay? So if x happens to be 1, then obviously we just take the derivative of that, and it would just be 0, but you know our x is going to be something like, in this case, like we had where it was 2x. So we're going to have to take the derivative of that. So it's a pretty easy theorem. Watch what I'm going to do right here. Okay, the theorem says I've got 2t plus 3, and whatever I have for my upper limit right here, that's going to go in for t. So I'm going to replace t with 2x. Doesn't matter what this number is down here. Okay, this is just a. This is just a constant. So I'm just going to plug 2x in for 2t, or for t, plus 3. So there's the f of x part. I've taken whatever's on the top of my limit, and or the upper limit, and I've plugged it into my function. So in this case we had 2x, I plugged it in. Now don't forget out here we have to multiply by the derivative of whatever our upper limit was. My upper limit was 2x, so I'm going to multiply by 2. Okay. Let's see what happens. I get 4x plus 3 multiplied by 2. Guess what? 8x plus 6. Same thing I got when I went through the process of actually finding the antiderivative, getting my function, and then differentiating it. When really all I had to have done, according to the second fundamental theorem of calculus, was put 2x there, and then multiply by the derivative of 2x, which is 2, and get to the same place. Okay? Now in this next example, what happens is, notice my limits are switched. Okay? So I have x squared on the bottom and 2 on top. But remember, we have a theorem that says, well, I can just put x squared on top, and then just take the negative of that. So I switch my limits, I take the negative of that. So now we can still apply the theorem. So I've got a negative square root. I'm going to replace the x right here, the t right here, with the x squared on the top. So I have the negative square root of 3x squared minus 1. And then I have to multiply this by the derivative of x, which ours was x squared. So I'm going to multiply by 2x. So f prime of x in this case is going to be equal to negative 2x times the square root of 3x squared minus 1. Simple as that, I'm done. Okay? Now the last example, we now have a variable on the top and the bottom. So my upper and lower limits are both variables. Okay? And then we're integrating with respect to another variable. Okay? No problem. I'll go through here and I'll apply the second fundamental theorem of calculus, which says I can take 3x and plug it in there, square it, minus 4, and I times that by the derivative of 3x, which is 3. Now, what would you normally do if you had a limit that was a definite integral? You would plug in the top limit and you would do that, and then you would plug in the bottom limit and you would subtract it. Same thing applies here. Now just do minus, okay, and apply the second fundamental theorem of calculus on your bottom one. So replace t with x and multiply by the derivative of x, which is 1. So I just did the second fundamental theorem of calculus with the upper limit and with the lower limit, and you subtract. So in this case I have 9x squared times 3, so I have a 27x squared minus 12. Over here I'll carry this minus through, so we have a minus x squared plus 4. We'll subtract, oops, put the x squared there. So we got 26x squared minus 8 is equal to our derivative. Okay? Second fundamental theorem of calculus. Pretty straightforward. If you have an integral of a function and you're trying to find the derivative of this function, we simply replace our t here with the function, and then remember to multiply by the derivative of our function. So in this case it was 2x, so we multiply by 2. Here, since it was switched, I just switched it back and put the x squared on top, made it a negative. Follow the theorem. Plugged in x squared, multiply by 2x, the derivative of x squared. When there's variables on top and bottom, apply the second fundamental theorem of calculus with the upper limit and with the lower limit, subtract them. Okay? Pretty straightforward theorem. All right, so kept it to about 20 minutes on this one. All right, so that's the second day of 4-4, and you're ready to start those problems.